Okay, thank you, Regina, for the very creative introduction. And I think you must be very relieved that I'm the last one that you have to introduce this semester. As you all can see from the left to right, this is a very unforgettable 5 years. And thank you for everyone coming to my defense. And I don't think in the history of CSAIL, we have ever had that many dogs in a thesis defense. Today, I'm very excited to share my recent research on robust machine learning. Machine learning, especially modern deep neural networks, are very capable at learning the associations between the input and output. As a result, biased data sets will lead to biased models. For example, to classify simoids versus polar bears, a model may either look at the causal features like the animals themselves, or utilize spurious features like the background. If this model has seen mostly simoids on grass, it may misclassify simoid in the snow. Here on the right is a real-world example on my Photos app. Apple thinks that the simoids are polar bears, like many of you. People have proposed many approaches to address this problem. For example, we can collect annotations for the bias attribute and use them to define different groups. Simoids in snow, simoids on grass, polar bears in snow, and polar bears on grass. By minimizing the worst case risk across all these groups, the model learns not to leave the minority groups behind. Did this solve the problem of robust learning? Obviously, not yet. There are two major limitations when we want to deploy this approach into practice. First, we need to know what are the biases a priori, and this is not trivial at all. Domain experts have to sit there and scrutinize the entire collection of data sets to find out what are the potential biases. Second, even if we know what are the biases, we still need to collect annotations for these bias attributes so that we can create the groups. And this process can be as expensive as collecting the label. We want algorithms that can deliver robustness without heavy annotation requirements. In this talk, we will look at 3 common scenarios and design algorithms for practical machine learning. Meta information, such as location and time, is often recorded when we collect the data. For example, we can have simoid images collected in the summer and in the winter. While they do not directly represent the bias features, such as the background, the level of spurious correlations may change. In this example, pictures from different times will have different background distributions. In the summer, we have more grass. In the winter, we have more snows. The spurious correlations here between the label and the background are different. But most importantly, a simoid always looks like a simoid. The causal mechanisms are the same. In this talk, we term these different data collections as environments. Here we have a summer environment and a winter environment. Given these environments, we would like to separate features with unstable correlations from features with stable correlations. By enforcing our model to only rely on those stable features, our model will be able to generalize better when the spurious correlations change. At this point, you may be thinking, can't we just train again to align the 2 environments? The answer is no. As you can see here, grass is positively correlated with simoids in both environments. Model will pick up this spurious connection even after we have aligned the feature spaces of the 2 environments. Invariant risk minimization, or IRM, is one of the most popular methods for this setting. In IRM, the idea is to learn a representation of the input such that, given this invariant representation, knowing which environment the input comes from cannot help you predict the label better. This objective makes intuitive sense because in order to reach this conditional independence, the representation cannot contain any information about the background. For example, suppose for contradiction that our representation encodes information about the background, grass. If we know that this image is from summer, then the likelihood of simoids will be higher. And the corresponding likelihood will be lower if this image comes from winter. However, this objective doesn't prevent our model from using biased features to build this invariant representation. In order to reach good prediction performance, neural networks will exploit whatever information that is available from the input to generate such invariant representation. To be more concrete, we can consider an extreme case where our learned representation collapses to the label of the input. By definition, this representation is invariant because knowing the environment will not provide any additional information about the label. However, we don't know whether our model uses the background or the sigmoid to produce this representation. And if these spurious correlations are different at test time, there's no guarantee on how this model will behave. As a result, IRM fails to deliver robustness in real-world applications. We take a different approach by decomposing robust learning into two steps: identifying biases and addressing them. We dub this algorithm PIE, predict then interpolate. First, we compare our data environments and identify the unstable correlations. Then we explicitly regularize the impact of these biases and train a robust model. How to identify the biases? Let's start with a simple thought experiment. If we take an environment and train a classifier, what will happen if we apply this classifier to make predictions on another environment? For a typical neural network, we can assume that the classifier F is powerful enough to recover the empirical distribution of the training environment. When applying this classifier to the testing environment, we're essentially comparing the two empirical distributions, which differ only in the spurious correlations. Intuitively, the mistakes of this classifier should be informative of the biases. If the unstable correlation is stronger in the training environment, the classifier will overuse this correlation. It will make mistakes on the testing environment when this stronger correlation does not hold. In this particular example, our classifier learns the strong connection between graphs and sigmoids in the training environment. And when making predictions in the testing environment, it fails to predict sigmoids when there is a snowy background. Now here's the theory for those of you who are interested. Suppose that the spurious correlation between the bias feature and label is bigger in the training environment than in testing environment. We show that when we use our learned classifier to make predictions, the bias feature will be positively correlated with the label in a set of correct predictions. And this spurious correlation will be negative in a set of mistakes. Let's go back to our previous example. On the left, we highlight the set of correct predictions in the yellow box. Here, seeing a grass background implies that the image will contain sigmoids. The presence of a grass is positively correlated with the label. On the right, among the mistakes, this spurious correlation flips to negative. Lack of grass implies sigmoids. While each single group is still biased, the spurious correlations have opposite directions across the two groups. And this is great, because if we can regularize our model to perform well on both groups, this model will have to ignore the background because that information is not generalizable. Grass implies sigmoids in the first group, but not in the second group. And snow implies sigmoids in the second group, but not in the first group. The model has to focus on the causal feature, the sigmoids themselves, to achieve good performance. To be more concrete, we would like to train our final robust model by using these groups that we have obtained from the previous prediction results. We compute the average loss of each group, and then we minimize the worst group loss during training. This optimization procedure is known as group distributionally robust optimization, or group DRO. It encourages our model to respect the minority group during training. Using linear programming, one can view this objective as minimizing the worst case performance over all interpolations of the given groups. From this perspective, our model delivers robustness because it has already seen a wide range of spurious correlations during training. To summarize, our PIE recipe has two steps. For each environment, EI-EJ pair, we train a predictor on EI and use this predictor to partition EJ into two groups: the set of correct predictions and the set of mistakes. We obtain our final robust model by minimizing the worst group loss. Our algorithm is model agnostic, and it has been applied to many different applications. Here, I would like to highlight our results on the text classification dataset asked to me. The goal is to predict whether a PubMed paper discusses the risk association between cancers and gene mutations, a standard binary text classification task. The challenge is that some cancers are more well-studied than others. As a result, models may utilize the presence of these cancers as a predictive feature, instead of relying on the causal feature, the risk association. Our goal is to learn a classifier that performs well across different cancer types. Here we consider two data environments, paper with breast cancer and paper without breast cancer. Constructing these environments can be done by simple keyword matching. Provided with these breast cancer environments, we would like to see whether our algorithm is able to reduce biases from other cancer types that are not known during training. Specifically, for each unknown cancer type, we partition the testing data based on the presence of this cancer and the label of the paper. For example, here we have lung cancer, and you can see 4 groups: label negative, lung cancer negative, label negative, lung cancer positive, and so on. We measure the average group accuracy and the worst group accuracy. In this example, while the classifier reaches perfect scores on 3 groups, it completely ignores the group on the lower right. Its average group performance is 75, and its worst group performance is 0. We compare our algorithm pi with 3 baselines here: standard empirical risk minimization, ERM, invariant risk minimization, IRM, and directly applying DRO over the training environments. Here are the results: average group accuracy on the left and the worst group accuracy on the right. The numbers here are average across all.
Imbalance. Like it's a group on which it makes mistakes. Very few examples. Can you, by trying to enforce it, work as well?
So here, like when we are doing the evaluation, so like we ensure that like each group like has like at least 5% of the data, and also like the bars that we plotted here are average across all cancer types. So it's kind of it doesn't like overfit, like the number doesn't overfit to the like, yeah.
The idea, it might be that the data itself this, like you make mistakes, like you just know there are very few cases, just know. That actually happens a lot in medical applications, where there are very few people who have the disease in comparison who don't have the disease. So in that case, wouldn't you, by trying to enforce the same performance of the 2 groups, because it's a statistic, because the smaller group with a few examples does not have enough statistical representation.
So I think like you can view this method as a smart way of balancing the labels. So like usually like when we just try to classification model and there may be like very few positives, and we may want to like upsample those like positive examples. And here like we're doing the same thing, but like our grouping by minimizing the worst by creating these groups, like instead of just focusing on the label, we are also taking care of these additional bias attributes. We can.
Yujia asking, do you have any empirical examples to demonstrate how much performance of the algorithm changes as the size of this minority overlay becomes higher?
So let me think. So here on Ask to Me, actually the number of positives is much smaller than the number of negatives, because like most papers are in PubMed doesn't talk about the risk associations. So I forgot the exact ratios, but it's like 20% or so. I forgot the exact ratios, but yeah.
I mean, this is a bit like not exactly for me. I'm talking about 2 centimeters that are really small.
I see. Yeah, we haven't done that yet. Yeah.
I think it's something that can be linked to the thesis analysis.
Okay. Yeah. Where are we? Okay. Here are the results. Average group accuracy on the left and worst group accuracy on the right. The numbers here are average across all 16 unknown cancer types that are not given to the model. As we can see here, all methods perform reasonably well in terms of their average group accuracy. But if we look at the worst group performance, the number drops significantly. RM performs only marginally better than ERM, and quite surprisingly, directly applying DRO outperforms IRM by 10 points. Finally, by contrasting different training environments, our algorithm Pi delivers the best performance. So how does Pi manage to reduce unknown biases? Here we visualize the correlation between the label and two cancers that are not given during training, colorectal cancer and ovarian cancer. The first row corresponds to the no breast cancer environment E0, and the second row is the breast cancer environment E1. Red means positive, blue means negative. As we can see here, while the directions of these spurious correlations are the same for each cancer, their magnitudes are different. Papers are less likely to contain risk estimates when breast cancer co-occur with other cancers. And when we apply a classifier trained on E0 to E1, the correct groups and the mistake groups have opposite correlations. This confirms that our previous theory generalizes to real-world applications. And these opposite correlations help the classifier to avoid using these spurious features during training. There is no free lunch, except here. On the right, I plot the running time of different methods. We observe that both DRO and Pi are much slower than ERM because of their min-max objectives. This additional time cost kind of makes sense here because the model needs to find out the true causal associations instead of overfitting to the shallow heuristics. On the other hand, the running time difference between Pi and the DRO is actually kind of small. So contrasting different data environments actually doesn't take too much time, but our gain in robustness is significant. In the first part, I've showed you how to learn a robust model when multiple data environments are available. While it is easy to collect annotations from multiple environments for resource-rich tasks, this procedure is infeasible for new tasks or resource-limited tasks. How can we deliver robustness in this situation? Fortunately, biases are often shared across related tasks. In our previous example, the label samoyeds and the polar bears are spuriously correlated with the presence of grass and snow. The same background bias persists when we want to classify a different set of animals, say squirrels versus penguins. I want to emphasize that while the examples here are picked for ease of illustration, this observation holds in many real-world applications. In natural language processing, the same gender bias exists in relation classification, name entity recognition, semantic role labeling, question answering, and so on. While we don't have access to multiple environments in our target task, in a source task, when training data is sufficient, we can use multiple environments to identify the unknown biases and transfer this knowledge to the target task. We present Tofu, transfer of unstable features. The algorithm has 3 steps: identify biases, transfer biases, and address biases. Here we don't reinvent the wheels. The first and last steps are the same as in our previous Pi algorithm, except that they now operate on different tasks. We identify biases by contrasting different source data environments. This gives us a set of groups with opposite spurious correlations. In the second step, we want to transfer this knowledge of biases to the target task and create groups over the target examples that are informative of the biases. Finally, we obtain a robust target model by minimizing the worst group loss. The question remains is how to create target groups that are informative of the biases. We have already learned that Pi can identify groups with opposite spurious correlations. In the correct group, grass implies samoyeds. In the mistake group, lack of grass implies samoyeds. If we take a step further, we can see that actually the background is grass for all correct examples, and the background is snow for all mistakes. Examples with the same prediction outcome share the same unstable feature. To better understand this observation, let's consider 3 different batches of examples: 2 from the set of correct predictions and 1 from the mistakes. We theoretically show that the bias features between the 2 correct batches will be more similar to each other. And this ranking similarity enables us to derive a representation that respects the distance of the bias features. Specifically, given the correct and mistake groups, we learn an unstable feature representation, F-bias. We first encode examples with F-bias and compute the distance between examples with the same prediction outcome. And then we compute the distance between examples with different prediction outcomes. We encourage the first distance to be smaller than the second one by minimizing the standard max margin loss. After training on the source environment, this representation, F-bias, learns to organize examples based on their unstable features. Now for the target task, we want to create groups that are informative of these biases. Given our learned unstable feature representation, we can simply encode these target examples and apply k-means clustering. These automatically derived groups correspond to different modes of the bias features, like grass or snow. By minimizing the worst case risk across all these clusters, we explicitly enforce our model to be robust against these biases. We applied our algorithm to 12 different transfer settings, and we observed significant improvement against previous state-of-the-art. Here, I would like to highlight our results on the image classification dataset, Celebrity. Celebrity is a large-scale dataset with 200,000 human face images. Each image here is annotated with 40 binary attributes. Some example attributes are gender, hat wearing, smiling, and so on. This dataset has been widely used in the robust learning community due to its rich annotations. Our source task here is to identify whether the person in the image wears glasses. We define two environments based on the age attributes, old and young. For the target task, we want to predict the hair color, blonde or not blonde. During training, our model only has annotations from old environment, and we would like to see whether the model can generalize robustly to the young environment. Specifically, we look at the 38 remaining attributes and evaluate the corresponding average group and worst group accuracy, as we have done in the first part of the talk. We compare Tofu with standard empirical risk minimization, fine-tuning the robust model learned from the source task, and multitask learning. For fine-tuning and multitask learning, we also played with different domain alignment techniques, including domain adversarial network, conditional MMD, and so on. All methods here use the same ResNet architecture. And here are the results. The numbers here are again average across all 38 face attributes that are not given to the algorithm during training and validation. Similar to the previous ask-to-me results, ERM is able to reach good average performance, but its worst group performance is only 61. Standard transfer approaches do improve, but the improvements are very, very tiny, only 3 to 5 points. By explicitly transferring the unstable feature representation, our model pushed the numbers far ahead by 18 points. We have learned how to reach robustness by contrasting different data environments or transferring.
Quite interesting. Did you try to look what were the unstable features?
Oh yeah, so on different data sets, we try to visualize. I don't have slides here, but I have pictures in the paper. So we visualize the clusters that we identified from Celebrity, and we found that one cluster has more gender, like male with blonde hair. The other has less male with blonde hair. So the model kind of learns to, by minimizing the worst case risk across these groups, model learns to kind of pay less attention to gender when it tries to predict the hair color. Yeah. 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 Okay. Now we have learned how to reach robustness by contrasting data environments or by transferring from related tasks. But what if we don't have this information? What if our data set only has a set of input label pairs? In this situation, how can we verify if our data set is biased? Or how can we learn robust models? Here we study automatic bias detection and propose LS, learning to split. Given a set of input label pairs, LS learns to split the dataset so that predictors trained on the training split cannot generalize to the testing split. This performance gap provides a proxy for measuring the degree of bias in the learned features and can therefore be used to identify unknown biases. Going back to our running example, while predictors can achieve perfect accuracy on the training split by using spurious heuristics like polar bears living in snowy habitats, they fail to generalize to the underrepresented groups, polar bears that appear on grass. Our algorithm list has two components, splitter and predictor. The splitter looks at each input label pair and decides whether this example should be used for training or testing. One can think of this decision as a latent variable that represents the prediction characteristic of each input. Note that here we don't have any explicit annotations on how to generate hard splits. Instead, our splitter learns from the predictor, whose job is to estimate the generalization gap across the given splits. Specifically, the predictor learns how to predict the label of an input by minimizing its empirical risk over the training set. To prevent memorization, we held out 1/3 of the training data for validation. After the training is done, we evaluate the predictor on the testing set. And this generalization performance guides the splitter to generate a more challenging split for the next iteration. To summarize, we can view our algorithm as a bilevel optimization problem. At each iteration, the splitter first produces a train test split of the dataset. Then we train the predictor on the training set and evaluate its performance on the testing set. Finally, we update the splitter to maximize the generalization error. The challenge, however, is that there are many trivial splits. For example, predictors cannot generalize if the amount of annotations is insufficient. Predictors will also fail if the training split contains all samoyeds, leaving the testing split with only polar bears. The poor performance of these trivial solutions arise from the lack of training data and label imbalance, and they do not reveal the hidden biases. To ensure that the learned splits are meaningful and well-defined, we impose two regularity constraints on our splitter. First, the size of the training split must be comparable to the size of the testing split. Second, the marginal distribution of the label should be the same across the splits. Our algorithm is model agnostic, and since it only requires a set of input label pairs, it can be applied to any supervised learning task, ranging from natural language understanding, image classification, to molecular property prediction. I would like to start with the natural language entailment dataset, MNLI. Yeah. In MNLI, the goal is to identify the relationship between two input sentences. Does one sentence entail or contradict the other? The dataset contains 400,000 human annotations and is one of the most common benchmarks for natural language understanding. Here we consider the standard approach, fine-tuning BERT, on random splits and LS generated splits. As we can see here, the same model that generalizes across random splits failed to generalize on splits produced by LS. And the train test gap is huge, 65%. To verify that our algorithm doesn't just end up with some trivial solutions, we visualize the label distribution of the learned training and testing splits. The pie charts on the left confirm that our regularity constraints are effective. So why are the learned splits so challenging for the predictor to generalize? While our algorithm only has access to the set of input label pairs, we see that the learned splits are actually quite informative of the biases previously identified by human. Specifically, in the generated training split, the top row, inputs with negation words are mostly labeled as contradiction. This encourages predictors to leverage the presence of negation words to make their predictions. These biased predictors cannot generalize to the testing split, the bottom row, where inputs with negation words are mostly labeled as entailment or neutral. Can we leverage these hard splits to learn a more robust model? The answer is yes. We can take the hard splits identified by our algorithm and train a new predictor by minimizing the worst split loss. Doing so enforces our predictor to discover features that are useful across the splits. Empirical results show that our method significantly outperforms the previous state of the art and is only 5 points behind the Oracle model, which has access to the bias annotations for all 400,000 examples. Finally, our algorithm delivers robustness beyond NLP on standard image classification and molecular property prediction benchmarks. Training with list identified splits significantly improves the worst case performance. The importance of data split has been recognized in many different applications. In molecular property prediction, we want our models to generalize across molecules that are structurally different from the training data. In medical imaging, differences in data collection can hinder model generalization across different hospitals. In biology, experiments are often confounded by uncontrollable technical artifacts, and it is difficult to draw conclusions across different data batches. Instead of relying on human-specified clues, our algorithm learns how to split directly from the annotations, and therefore it can be applied to scenarios when such human knowledge are not available or incomplete. And this concludes my presentation. Before I take questions, I would like to thank everyone who has supported me in the past 5 years. And first and foremost, I want to thank my ladylike advisor, Regina. Over the 5 years at MIT, she encouraged me to expand my horizon every single day. I cannot remember how many times she smiled knowingly and told me, continue thinking. Whenever I propose a project, she challenged me to think more critically, more creatively, the perfect discriminator to train my idea generator. As an international student, I sometimes feel homesick, and Regina has always been like a mom to me. She taught me to eat healthy and live healthy. When I decided to raise the boys, I told her. When I composed a piece of music, I told her. But when the plant she gave me passed away, I didn't tell her. Yeah, so there's some tragedy happening, like, yeah. No, like they kind of suffer from like scale or something, like, anyway. I'm forever grateful to have her as my advisor, and I feel so happy that I will be still staying around after graduation.
You run 5K.
Oh, yeah, I run 5K. I want to thank my thesis committee for taking the time and effort to read my thesis and give me feedback. Dina and Regina are the smartest women that I know. Doing research is not just about publishing papers. When talking to Dina, I can see her visions for the future of mankind. I'm very excited about my future at MMRO. Hogan and I have been working on the Air Force project for 3 years. Yeah, he's very sharp and sweet, the kind of person that I want to be. I want to thank all my friends, lab mates, and collaborators. Thank you all for creating such an amazing atmosphere here. We had so many insightful discussions and so much fun. Special thanks to Eliza and the White Nebula family. They're here. Thank you for bringing the clouds to my life and supporting me all the time. Thank you, Rachel, Tofu, Yumi, Saber, and Manchichi. You're the apples of my eyes. Together, you're my home. I want to thank my parents and family in Shanghai. Thank you for making me who I am today. I really, really miss you. Okay, finally, thank you for all coming to my defense. Now I will open the floor for questions.
Hey, what a beautiful presentation with